Welcome to Session 2 of Sampling for Forensic Practitioners, a short course sponsored by NIST. If you missed Session 1, you can find that on our YouTube site. Your presenter today is Distinguished Professor and President's Chair in the Department of Statistics at Iowa State University, Dr. Alicia Carriquiry. She is also a co-founder and the director of the Center for Statistics and Applications in Forensic Evidence. We appreciate her joining us again today for the second session. And Alicia, I will turn it over to you.
We were talking about sampling methods. So we discussed the importance of, we discussed all kinds of things. We motivated this idea of sampling, why sampling is important. We talked about the fact that random sampling will allow us to make inferences from the sample to the population. We also discussed the attributes that a good sample should have. And then we talked about methods, sampling methods, so that we know we will get a reasonable sample. So today we're going to talk about two major topics. One of them is, what do we do with the sample information once we have collected the data? And here the problem is the following. All the statistical methods you've heard about, estimating a standard deviation and so on and so forth, will apply under this ideal scenario where you have a very large population, a tiny fraction of that population included in the sample, and furthermore, sampling is with replacement. In real life, your populations are not so large. Sampling is done without replacement. And so the calculations that we carry out using the sampled items require a little bit more attention. So, remember we introduced this a finite population, did we? Yes, we introduced this finite population correction factor. That's going to come in pretty prominently in almost everything we do today. So today we're going to talk about inference, what we do, how do we manage to say something about the population using the sample items we have. And then we're going to talk about sample size calculation. And this is another big item. How big a sample do I have to draw in order to satisfy some criteria that I will set for myself? And then on next Friday, we'll talk about Bayesian versus classical or frequentist approaches to sampling. We won't spend a whole lot of time. Maybe if I can, I'll say something about bulk sampling or composite sampling. And then most of the time, Joe will actually go over a bunch of examples and show you how to use software and essentially put everything into practice. So let me get started. So remember the big picture, right? So we have a population, we draw a probability sample, and we use probability theory to get a probability sample. And then once we have this sampled items, we want to infer something about the population. So we want to learn something about the population using those sampled items. And so there's many, what do you mean by inference? There's many different types of inference we might want to make. Essentially, this is what kind of questions do we want to answer? And when we think about inference, remember we talk about populations and parameters and samples and statistics. Statistics, we talked about them as being, statistically justifiable guesses of these population parameters that are unobservable. We often talk about point estimates, which is when we just obtain a value of a statistic, but much better are what we call interval estimates, which is essentially a point estimate plus some uncertainty estimation that is attached to it. So this is when we say, my estimate for the population mean is something plus minus some margin of error. And today what we're going to talk about is two types of population summaries. One of them is a proportion, the population proportion, and the other one is a population mean. And implicit in the population mean is a population total. So a population proportion is, this is when I have items that can either be, let's say, positive or negative. So contains drug, doesn't contain drugs, is a fraudulent operation, is not a fraudulent operation. Sometimes we have more than two categories, and it's pretty similar to the case where we have two categories. But in this case, I'm going to talk about items that are positive. And by that, I mean exhibit the attribute that I'm thinking about, and items that are not positive. In other words, they don't have the attribute we're talking about. The population mean, this typically, we are going to be interested in means when the attribute of interest is not categorical like above, but continuous. So the weight of something, the dollar value of something, the amount of radiation in something. So this is where we are going to think in terms of means rather than proportions. And this is what I was saying before we started, the spoiler alert. When we have a very large population and we have simple random sampling, and in this case, we can assume sampling is with replacement, nothing changes. So everything you've learned in stats, how to compute a mean, how to compute a standard deviation, how to compute a confidence interval, it's all the same. The problem is when we have a finite population, so relatively small n, and then we have to worry about this finite population correction factor. So this is where we have to be a little bit more careful, because typically not only do we have a finite population, almost all the time we sample without replacement. And this is where things get complicated, and we have to be careful about what we do. They don't get complicated. We just have to be aware of what we're doing. All right. And we talked last time about multi-stage sampling. And remember we said first sample a cluster, then within the cluster, for example, that would be a primary sampling unit. Then within the cluster, measure the secondary units, the secondary sampling units. In those cases, we'll give an example in this particular case, but here we have to worry about the design at the sampling approach at each stage in the sampling process. How do we pick the clusters? How do we, for example, we could have picked clusters using a stratified design. You can nestle things one inside the other, and that's perfectly fine to do as long as you keep track of what you're doing at each stage. Okay, so let's start with the population proportion. And typically people talk about, this is a parameter because it refers to the population, and oftentimes we call it pi. Sometimes you'll see it called p. So just make sure you understand the context. I'll call it pi here all of the time. And this simply is the proportion of items in some population that exhibit whatever attribute it is I'm thinking about. And how do I do inference? How do I learn about this population proportion from a simple random sample? Well, pretty intuitively. So I have a sample of size little n that I picked in some way, a simple random sample in this case. I can get a point estimator, so a good guess for pi simply by computing the statistic p, and p is just the number of the items in the sample that exhibit the attribute divided by the number of items in my sample. So this is what I was just saying. Sometimes if people call the population proportion p, then they might call the sample estimate, they might call it p hat. Or sometimes if people call the population proportion pi, They might use pi hat instead of p. So make sure you understand the context so that you know whether p refers to a statistic or to a parameter. If people that are writing have any consideration for their readers, it should be obvious from the writing. All right, so let's do an example. Suppose that the population consists of 100 tablets in somebody's duffel bag. And for now, we don't know this, of course, but let's suppose that 40% of those tablets are positive. So they contain some illicit substance, and the other 60% are just placebos, fillers. They are just to confuse you. So we don't know that, of course, but we would like to estimate from a sample of those 100 tablets, how many of those tablets are positive. So here, 0.4 is pi, and pi, of course, is unknown to us unless we were to analyze every one of those 100 tablets. But let's suppose we draw a sample of size 10, and in this case, we just use a simple random sample. And let's suppose that I analyze those 10 tablets, and I find that 5 of those contain some illicit substance, and 5 of them don't. So here, p is just 5 divided by 10. So the number of positives in the sample divided by the sample size. And so my point estimate, this is the statistic, the sample statistic. So my point estimate is 0.5. That's my best guess of the value of pi, okay, or 50%. So obviously, 50% is not the same as 40%. So in this case, p is not equal to pi. And the truth of the story is that unless you are crazy lucky, in general, pi is not, or p is not going to be the same as pi. And so the question is, how do we know if p is any good? So is it even a good guess for pi? How close can we hope p is going to be to pi? So this is where, remember, we started this course thinking about this idea of sampling uncertainty or sampling error. And I told you this is not an error. We should think about this sampling uncertainty. The idea is pretty obvious, right? So if I have 100 tablets, there's many different sets of 10 tablets that I could have sampled. And we talked about this earlier on, how many, if we use sample without replacement, how many samples of size 100 can you get from a population, of size 10, can you get from a population of size 100? And there's thousands and thousands of them. So if I think conceptually about drawing many different samples from this population, and in each one computing the statistic, p, then I know there's going to be variability from sample to sample. So in one sample, I might get p equals 2.5. In another one, I might get p equals to 0.38. In another one, 0.38. In another one, it might be 0.43. I don't know. So there's going to be variability. And this is what we call the sampling distribution of the sample proportion. There's a distribution of possible values of p that I would get to see if I were to obtain many samples of size 10 from this population of 100 tablets. So the standard error of p, in other words, the variability of these p's that arises in repeated sampling, this is what I need to compute to get an idea of how close any one p could be expected to be from the true pi. So remember two things, right? Typically, I only have one sample. So it's not like I can get a million samples. Typically, I work with one sample. And second of all, I do not know pi. And so the question is, what can I say about p? How close can I hope to be if I have this one sample from which I compute this one p to the true value pi, which I don't know. So here's a little illustration. So this is that population of tablets. There's 100 tablets. The dark blue tablets are the ones that have this illicit substance, and the light blue tablets, these are the ones that are sugar tablets. And there's 40% of them, so 40 out of 100 are bad or positive, and 60 out of 100 are innocent. So let's suppose I take a bunch of samples. I take little m samples, and in each one of those, I compute p. And so in the first one, which is the sample I got to begin with, I had a p of 0.5, the second one 0.3, the third 1.4, and so on and so forth. Let's suppose that in the mth sample, I had a p of 0.3. So how do I compute the standard error of the estimator? The standard error of the sample proportion is computed as p times 1 minus b divided by the sample size. And because I have a finite population and I am sampling without replacement, I have to multiply by this thing called the finite population correction factor. So this finite population correction factor is computed as a ratio. Sometimes you're going to see it as n, the population size minus the sample size divided by the population size minus 1. Sometimes you're going to see it as just divided by the population size. And it's more or less the same. And so see what happens, right? Let's suppose n is very large. Then if n is very large and the sample is relatively small, this factor is close to 1. And so I can totally ignore it. So when I have a very large population, this finite population correction factor is close to 1, and we ignore it. And this is what we do in almost in all standard statistics, where we are assuming that we're sampling from an infinitely large population. When in this particular example, we can actually compute the finite population correction factor. It is the population size, which is 100, minus the sample size, which is 10, divided by the population size minus 1. And if you take the square root of that, it turns out it gets you 0.95. So the standard error of the population proportion, when you have a finite population and are sampling without replacement, is the usual standard error, which in this case is 0.158, times this finite population correction. And so we're getting 0.15. If I was not taking this course and I didn't know about this finite population correction factor, which is always less than 1, by the way, I would have gotten that the standard error was 0.158. And so I would have been overestimating the true variability of my estimator. In other words, I would have been more pessimistic in that sense than I need to be, because I would have thought that there was more variability in my sample estimator than there truly is. So how do we compute what we call a margin of error? So a 95% margin of error for the sample proportion is computed as follows. The margin of error, which we will denote by ME, is simply 1.96 times the standard error of P. So in this case, the margin of error is 0.3. I use 1.96 here because I'm computing a precise margin of error. Oftentimes, including myself, will use 2 instead of 1.96 and obtain an approximate margin of error. It's pretty darn close. So how do we, so then what I can compute is an interval estimate for P. And that interval estimate would be P minus the margin of error. That's the lower bound of the interval. And the upper bound is P plus the margin of error. So in this case, well, okay, so that's how you compute it. In this case, you get 0.2 to 0.8, which is pretty wide. And so how do I interpret that? I am 95% confident that the interval that I just computed contains the true value of the population proportion. So the interval sample statistic plus minus margin of error, when the margin of error is computed in this way, is a 95% confidence interval for the population proportion. If instead of a 95% margin of error, I wanted a 90% margin of error, this value 1.96 would have changed to 1.65 or 1.645. And so the confidence interval would have been a little narrower, but because I would have been less confident that my narrower confidence interval actually does cover the true population proportion. And if I want to be super confident, let's suppose I want to be 99% confident that my confidence interval actually covers the true proportion, I would have to look it up, but I think it's 2.54 something that would go in here. Okay. So here's visually. So, okay, so one thing that we noticed, why did I was really careful when I said I am 95% confident that the interval covers the true value of pi. I didn't say the interval covers the true value of pi with 95% probability. That would have been wrong. Why is that wrong? Because in this conception of the universe, which we're talking as if we were all classical statisticians, the value of pi is fixed. That's number one. The only thing that is random is the actual interval. Why is the interval random? Because if I had gotten a different sample instead of the one I got, my standard error might have been different. Let's suppose that instead of this particular sample, I have gotten one where my estimate P was 0.4. Then the standard error would have been different, right? It would have been 0.4 times 0.6 divided by 10. And so the margin of error would have been different and the interval would have been different. So this interval is like P changing from sample to sample. And so that's, and you know, in any one realization, so in my sample, in any one sample, this interval either covers or doesn't cover. There's no 95% about it. The interval covers or doesn't cover. And the question is, if I were to compute 100 intervals, how many of those would cover? And that's where the 95 comes in. I would say 95% of those would cover. I don't know whether my interval covers or not, but I know that I have a pretty good chance that it does because 95% of all intervals would cover the true value pi. So this is the same story, but visually, imagine I draw 1,000 random samples from some population and compute the 90% confidence intervals. What I'm showing you here is the last 50 of those 1,000. So this is number 950 all the way to number 1,000. And let's suppose that in this example, the true population proportion pi is 0.6, and that's marked, or 0.61 or something. And that's marked by this yellow line over here. And so each of these horizontal lines represents a 90% confidence interval, one from each of the last 50 samples out of the thousands. The little triangle here is the estimate P obtained from each one of these little samples. And if it's a 90% confidence interval, I would expect that out of 100, 90 intervals would cover the true value of pi and 10 would not. So out of 50, I would expect that 45 would cover and 5 would not. And so the red here are those intervals that don't cover the true value of pi. And there's 7 of them instead of 5, but that's close enough for government work. If I had looked at a different set of 50, I might have found, 4 that didn't cover. And so this is visually what is going on. Now, my sample is one of these. I don't know which one it is. And so in my sample, for example, I may be unlucky and get one of these red samples, in which case I'm nowhere close to the true pi, or I may get super lucky and get, for example, the bottom one here, where my p is right on the nose. And I don't know that. Okay. So the interval estimator then for the population proportion pi is just p plus minus the margin of error. And again, if I compute the margin of error using 2, then I get a 95% confidence interval. If I use 1.645 instead of 2, then I get a 90% confidence interval. And so this is, I think, best practice. Always attach a margin of error to your estimates, because that will give your reader an idea of how much weight to put on your estimate of this unknown population quantity. In this example, with a sample of size 10 from a population where the pi, the true pi, is close to the middle of the distribution, so it's close to 0.5, the margin of error was really high. And so that was kind of, if I tell you, I know that the true proportion is between 0.2 and 0.5 with 0.2 and 0.8 with 95% confidence. I'm not telling you a whole lot, because that interval is so wide. You'd be amazed at how why, if you go back and look at some publications that appear in the literature, and where people give you a point estimate and make all kinds of fuss about this point estimate, we got a point estimate. Well, you'd be horrified to know that if those people had attached a margin of error to that estimate, you would have been probably much less confident in their results than you might have been. Sometimes we talk about a relative margin of errors, and those are based on what's called the relative standard error. And that simply means I screwed up here. What do you know? Take the standard error and divide by the square root of p. So that should have been the square root of p. And so wrong calculations, but in this case, I got 30%. And so that seems a little bit less horrific, in the sense that sometimes if you express the margin of error in relative terms, you realize that it's not so bad. So the standard error of the sample proportion is affected by 2 things, actually. Let me go back to the formula. It is affected by the value of p and also by the sample size. The closer p is to 0.5, the closer the true pi is to 0.5, the larger the standard error is going to be. And the smaller the sample size, the larger the standard error is going to be. So there's nothing you can do about the true proportion in the population, such as life, but you can do something about minimizing the standard error or maximizing the accuracy of your sample estimate by playing with the sample size. And we'll talk about that later today. All right. So for example, in this same example, and we'll talk about that later today. But in the same example, if instead of having a pi of 0.4, I had a pi of 0.9, and I had gotten, so that would be the true proportion of positives in the population. And instead of getting a p of 0.5, I had gotten a p of 0.8 in the sample, then the with the same sample size and the same finite population correction factor and everything, my standard error would have been 0.12. So a whole lot lower than it was earlier. And again, this is not correctly computed, but if I were to do this particular calculation, I would have cut my standard error in half, my relative standard error in half. So I would get something that's about 15%. And the margin of error here would be 0.24. So in this particular case, I get something that's more informative, because in this case, I can tell you that I'm 95% certain that the interval 0.56 to 1 actually covers the true proportion, the true population proportion. It's still kind of iffy, but at least, I mean, to do anything better here, I would have to increase the sample size. But at least it's better than the one we had before. So now I hope that everybody had a very good night's sleep and lots of coffee this morning, because I need to get into the statistical weeds for many of the things that come next. And so bear with me, and if you have questions, make sure you put them on the Q&A so that Joe can address those questions in real time. We're going to talk statistics now, a little statistics. So we're going to have to do some statistical foundations to understand some of the things that follow. So in sampling, people use, so far, I have not talked at all about probability models. You know, the normal model, the binomial model, the Bernoulli model, I have not said a single word about anything. The only thing I've talked about is, you know, we're interested in proportions when we have a categorical random variable that we're trying to measure, and we're interested in means or some other summary along those lines when we have a categorical, a continuous attribute. Sampling is often relying on what's called the design. So sampling is often design-based. And so we talked about different sampling designs. So far, we've been design-based too. We talked about the simple random sampling design, the stratified design, the clustered design. So we've been thinking in terms of design, sampling designs. Now I'm going to take a little bit of a detour into a different approach to thinking about sampling, and that is what's called the model-based sampling approach. And so, what did I do? Okay, here we go. And so now I'm going to talk a little bit about statistical models. So let's suppose I'm still in the categorical world. So I have my random variable, the attribute can take on only two values. So positive and negative, let's say. And so one good probability model, one statistical model for that type of variable is the Bernoulli model. And the Bernoulli model simply says, so how do I read this little thingy here? I say, Y has a Bernoulli distribution with success probability or probability of positives or, you know, probability pi. So what does it mean? If I have a big bag full of Y's, you know, imagine a big bag with balls that are positive, label negative, and I stick my hand into, and you know, and pi, the proportion of positive balls in that bag is pi, and the proportion of negative balls is 1 minus pi. Then if I stick my hand into that bag and draw one Y, I have a probability pi of observing a positive Y and a probability 1 minus pi of observing a negative Y. So this is a very basic statistical model. And, you know, pi is called also the expected value of Y. So why is it the expected value of Y? Well, for exactly the same thing I just said, right? If I stick my hand into the bag and I know that a proportion pi of those balls are positive, what do I expect? I expect that when I draw one of those values, I am going to get a positive with probability pi, and I'm going to get a negative with probability 1 minus pi. It turns out that the population variance is pi times 1 minus pi. We're not going to go into deriving these things, but the expectation or the mean is pi, and the variance of y is pi times 1 minus pi. These are all population parameters. Now, I'm still in the weeds, and I'm going to be in the weeds for a little while. So let's suppose that I take a sample of n independent Bernoulli variables. So instead of observing a single y, I am going to observe n of those. And for now, I am thinking sampling with replacement. So I stick my hand, I grab a y, I see whether it's a 1 or a 0 or a positive or a negative, I throw it back in. I get another one and do the same thing, throw it back in. Each one of those y's has a probability pi of being positive. If I look at, so now I have a sample of size n of values of y, y1, y2, all the way to yn. Some of these are going to be ones, some of these are going to be zeros, or some of these are going to be positive, some of these are going to be negatives. X here is the sum of all those values. So essentially it is the number of positives. If the negatives are zeros, they don't count. So it's the number of positives I observe in a sample of size n. And if y, a single y, is a Bernoulli random variable with probability of success pi, this x variable, which is the sum of all the positives in a sample, actually I should say the number of positives in the sample, that's going to be a binomial random variable with fixed n and probability pi. So simply says is if I have n trials, in other words, a sample of size n from this population, where each item in the population has equal probability of success equal to pi, then x is just this, has this statistical model. And the expected value of x is intuitively just n times pi. So it is the probability of success of any one y multiplied by the number of y's I got. So by the sample size. And the variance is just n times pi 1 minus pi. This is all fine and dandy, but it only applies when sampling is with replacement or when n is very, very, very large. So, well, what do you know? So if, remember my sample, dang it, sorry. So remember my sample estimate P for pi. So P here is just the number of positives divided by the sample size. So the number of positives here, remember, has expected value and n times pi. And so if I want to know what the expectation of my P is, I take the expected value of x divided by n, and that gives me pi. So it's n times pi divided by n, I get pi. Why do I care about this? Because this tells me that my pi, my P, if I compute it in this way, if I compute it in this way over here, then P has this wonderful statistical property, which is unbiasedness. On the average, my P is going to be equal to pi, or is going to be pretty darn close to pi. The other nice property that this point estimator has is consistency. What does consistency mean? Well, let's look at consistency. Essentially means that as my sample size increases, my P gets closer and closer and closer to the true pi. And so how do I look at consistency? So I look at the variance of P, and the variance of P is just the variance of x divided by n squared. Did I use this last time around? I told you that the variance of a constant times a times a random variable is equal to the constant. Oh, here it is. So to what rule did I use here? There's a rule that says if z is a random variable and a is some fixed number, then the variance of a times z is just a squared times the variance of z. So here the 1 over n is playing the role of a, and x is playing the role of z. And so the variance of p is just the variance of x divided by n squared. And if you just plug in, you get this expression over here. And look what happens. As the sample size increases, the variance of p goes to 0, so decreases. In fact, for a super, super, super large n, this ratio becomes really small. And so it means that the larger the sample, the smaller the variability of my sample estimate. And that property in statistics is called consistency. So P, computed in this way, has two very nice properties. It's unbiased and it's consistent. So it's a good thing to compute. And the standard error is just the square root of the variance. And so that's what the standard error of P is. And you see, this is exactly what we had gotten when we were looking at simple random sampling from an infinite population with replacement back in slide 73. This is I can arrive at the same result in the two ways, either using this design-based approach or this statistical model-based approach. Okay. So now I'm really going to dive into the weeds. What happens when I have a finite population and I am sampling without replacement? And so what happens is that this absolutely beautiful little model that we just talked about no longer applies, because the number of positives x in the sample is no longer a binomial random variable. In fact, but that's the bad news. The good news is that we have a different model that we can use in that situation. And that model is the one that's called the hypergeometric model. So the hypergeometric model depends on, so remember the binomial model depends on the sample size n and on the probability of success pi. This hypergeometric distribution depends on the sample size n, yes, but it depends also on the population size and on the number of positives in the population. And so remember, and so we didn't have to know x and n in the binomial model. We could, it sufficed for us to know the ratio of those two. So if we knew pi, we would be golden. Here we have to know x and n. If we know x and n, of course, we would know pi, but this is what this model depends on. So, so to contrast these two approaches, both of these models, the binomial model and the hypergeometric model, are used to describe the behavior of a random variable that can take only two values, positive, negative, 0, 1, whatever. And both, in fact, describe the number of events or the number of positives that I can observe when I have a fixed sample size equal to n. But there's a big difference. In the binomial model, the probability of success pi is the same for every observation or for every sampled item, whereas in the hypergeometric model, when I am not assuming that I'm sampling with replacement, in fact, I am sampling without replacement, the probability of success is changing from trial to trial. And we talked about this a little bit in last Friday. And so let's just, why is it changing from trial to trial? Because if I draw an observation, I draw an item from that population and do not put it back, then already the number of observations in the population changes to big N minus 1, because one of them I took out already and cannot be sampled again. And of course, if the item I sampled was positive, then it means I have one less positive in the population. So the proportion of positives is now different in the population than it was to begin with. And so the probability of success is going to depend on what have I, or so the probability of success, let's say, of the 5th item I draw from this population is going to greatly depend on what the earlier 4 items I took out already look like. And so it turns out that if X here is a hypergeometric random variable with success probability pi, the expected value of X is just the sample size times the number of positive. So if pi here doesn't mean success probability, this means that the proportion of positives in the population, then the expected value of X is just N times pi. The variance of X gets a little bit more complicated. So the variance of X happens to be calculated as follows. So this is N, which is the sample size. Then X over N is the number of positives in the population. N minus X over N is the number of negatives in the population, times the finite population correction factor. So we end up with something that looks like this. And so in practice, if we want to, so if you happen to have a relatively small population and you're sampling without replacement, and you are computing P the same way we computed before, so the number of positives in the sample divided by the sample size, then when you compute the standard error of P, you have to be careful. And the formula you need to use is this one that we have over here. So the standard error of P is just going to be equal to the square root of this thing divided by N squared. And so this is what that standard error looks like. And here is what that population correction factor is, it's sort of built in because we're using the appropriate model for the case where we have a finite population and we sample without replacement. Okay, so that was what I wanted to say about the finite population correction for the population for the sample proportion. Now let me move to the population mean, mu. This is when we have a variable that is continuous, like the weight of something, the dollar amount of something, the length of something, whatever. All right. So this should not be hard. So now let's suppose that, again, we have 100 tablets, but now what we're looking at is not whether they're positive or negative, but rather we're taking the weight of some controlled substance in those tablets. And so what we want to do is we want to estimate the population mean, mu, we call it, of the substance in those 100 tablets. And so let's suppose we draw a simple random sample of size 5 without replacement. And let's suppose that I analyze those 5 tablets and I get these values in grams, let's say. 1.2 grams for the first, 1.98, 0.95, 116, 104. So the sample mean is computed in the usual way. So we call this Y bar, and that's just the average of the 5 measurements. And in this case, it's 1.066. So this is my best guess, or the point estimate of the average weight of this substance in all 100 tablets. So if I take any other tablet, so this is what I get, my best guess for any tablet in that population is going to be. It turns out that the sample mean has, there's many other estimators I could have gotten. I could have said, I'm going to guess that the value of mu is 1. That's another estimator from you. It's not a very good one though, unless you get crazy lucky, but it doesn't have any good statistical properties. Another estimator might be the median of all these values instead of the mean. It doesn't have as good, that the median is also pretty reasonable. The mean is the one that has the smallest margin of error, but the median is more robust, meaning if I had an outlier value here, some crazy value, let's say one of these values was 5, which is totally different from all the other ones, the median would not be terribly affected. The mean would be very much affected. Okay, so the same question I asked myself, how good an estimate of mu is y bar? And the same story, right? So unless we're very lucky, mu is not equal to y bar. And so that's not what I'm going to say. And so what I want to estimate, what I want to do is first of all, I hope that my sample estimate is close to mu, and to decide how close it is, I'm going to have to estimate the standard error of y bar along the same lines that we did with the standard error of p. So again, there's variability because the sample mean y bar varies from sample to sample. So if I were to take different samples from the population, I would get different values of y bar. And again, we're going to quantify the variability of y bar using the standard error of y bar. And because we're thinking about finite populations and sampling without replacement, the standard error of y bar, when we compute it, has to be corrected by the finite population correction factor. And so here the standard error is just the standard deviation computed from all those observations divided by the square root of n times the finite population correction factor. And this S you compute in the usual way. You just take the deviation, it's the average of the squared deviations of each observation from the mean in the sample divided by n minus 1 and then square root of that. So what does this depend on? So the standard error of the sample mean depends on n. So the n comes in here. It also depends on S, which is the variability in the, so S here is an estimate for the population variability of this attribute. And so if every tablet is more or less in that population is more or less the same and has more or less the same amount of this substance, then S is slow because there's little variability of this attribute in the population. But if these tablets are all over the map, some are heavier, some are lighter, some have more, some have less, then the variability of the attribute in the population as reflected by S, as estimated by S, is going to be larger. So there's, again, there's not much I can do about the natural variability of the attribute in the population. I just need to keep it in mind when I decide on the sample size, because the more variable the attribute in the population, the larger my sample size is going to have to be if I want to have a small margin of error. So again, the margin of error approximately is simply computed. The margin of error for the sample mean is just 2 times the standard error of the mean. And so a 95%, and I'm using the 2 here, so it's approximate. So a 95%, an approximate 95% confidence interval for the population mean is the sample mean plus minus the margin of error. All right, so in our example, we can compute this relatively easy. So the first thing we need to do is remember the y bar was 1.066. I had a sample of size 5. So the first thing I need to do is compute S, and S is just each observation minus the mean squared. All of those squared deviations added up and divided by n minus 1, which is 4 in this case, and I get 0.11. The finite population correction factor is 0.98. And so the standard error and the margin of error for y bar is 0.048 and 0.096. So what can I say? I can say that with 95% confidence, the interval 1.066 plus minus 0.096 will cover the true average weight of that substance per pill in the population. And here's the same illustration that I showed you earlier. So here we have a situation where we have 100 samples of size 3, and the true mean here, mu, is 10, and that's denoted by this red horizontal line here. And I would expect that about, and this is just simulation, each one of these vertical lines is an interval, and each one of the black dots here represents the Y bar that was computed from that particular sample. And so what you can see is that most of the intervals cover the true value of mu, except for this one in red, this one in red, this one, this one, this one. So I would expect 5 out of 100 not to cover. And in fact, in this example, we got exactly 5 out of 100 that didn't cover. So what's coming next is I'm going to talk about the estimating the population mean, or making inferences about the population mean when we have, not a cluster sample, a stratified sample. And then when we have a cluster sample, I might go through the calculations a little fast because I'll point you to places where you can actually read more about this. It just gets messy, and you're never going to do this by hand anyway. So just so that you know where these things are coming from. All right, suppose that we have a stratified sample. Remember a stratified sample? This was when you took the population and you had a heterogeneous population with different subgroups. And so those groups, each group is what we call a stratum. And what you want is you want to make sure that all of those groups are represented in your sample. So what you do is you first stratify and then you draw observations from each one of those strata. And so calculations are pretty much the same. It gets a little messy because we have to keep track of which stratum we're talking about. So if we're talking about the stratum labeled H, then the mean in that particular stratum is computed in exactly the same way, right? So you take all the items you sampled from that stratum, measure the variable of interest, divide by the sample size you drew from that particular stratum. And so again, this is written in all kinds. So Y sub HI here is the ith sampled item from the H stratum in the population. And so the stratum sample mean Y bar here is an estimate of the population mean for that particular stratum. So imagine, so everything that we just said for simple random sample applies here within a stratum, assuming that you're doing simple random sampling within strata. And so that's an estimate of the stratum population mean. And so how would you compute the overall population mean? Well, the overall, or how would you estimate the overall population mean? That's this Y bar I am calling Y bar STR for stratified. And that's just a weighted average of the strata means. And the weights here are given by the relative size of each stratum in the population. So this expression, so you take for each of the stratum the stratum size divided by the population size and multiply that by the mean that you computed in each stratum. And this is implicitly assuming actually that we have, remember we talked about how do we allocate the total sample size to the different strata, and we said a common approach is to use this proportional to size allocation. And this is implicitly assuming a proportional to size allocation. And so the only thing I did here to simplify the notation a little bit is I took this NH divided by N and called that WH, just to show that this is actually a weighted average. So it's you take each stratum average, and then weigh them, multiply by this proportion, and then add them all up, and that gives you your point estimate of the population mean. And if you would like to read more, in fact, they use a very similar notation, so it's not, it's kind of easy to follow. Go to this ASTM 1402, published in 2013, section 8. It gives a nice discussion of this. All right, so the standard error, this is pretty much the same thing we did before. So within each one of the strata, we can compute the standard error of y bar, just like we did before. So if I were to take, whoops, sorry. How did I compute the standard error of y bar? I used this formula. And so I can use the exact same formula within each one of the strata. So I would get one standard error for each y bar. And the question is, how do I combine them in order to get the standard error of the overall y bar, the y bar STR? Well, you end up with an expression that looks horrific, but it's really not that bad. So what am I looking at here? So the standard error of y bar STR is what? Let's start with this piece. This is just the variance of y bar in the H stratum. So that's the same formula we had before. This is the population correction factor for the H stratum. We don't have the -1 here, but it doesn't matter. So it's the population correction factor. And this here is that weight. So essentially, we're doing the same thing here. We're taking the weighted average of all the stratum level variances, weighted average, corrected by the finite population correction factor, and then taking the square root of that. So it looks ferocious, but it really isn't ferocious. It's just another weighted average of, in this case, stratum level variances. So here's a little example. So let's suppose we're looking at financial audits, and we have in a desk, we find 1,000 transactions, and the transactions appear to be of 3 different types. Let's suppose real estate, futures, something else. And let's suppose that out of 1,000, there's 200 of type 1, 500 of type 2, and 300 of type 3. And let's suppose that we sample proportional to size at a constant rate of 5%. So the sampling fraction here is always 5%. And so 5% of 200 is 10, 5% of 500 is 25, 5% of 300 is 15. And so my total sample size here is going to be 50. So, and let's suppose that the measurement of interest is the dollar value in millions of dollars of each one of the sample transactions, or of each one of the transactions. And the goal is to estimate the average dollar amount in millions of all of the transactions in this, all 1,000 of the transactions in this particular operation. So you have access to this invented data, and it's called financial audit.data. So you can reproduce everything that I'm doing here. This is an Excel sheet with all the calculations already programmed in. And so the first thing we do is compute the 3 stratum means, and those are these values, remember, all in millions of dollars. And then we compute the 3 standard deviations, 1 for each stratum, and this is what I get. And now I can compute the standard errors for each of the 3 strata means. And so that's just divided by the square root of the sample size in each one of those cases, and those is what I get. So now I have everything that I need to compute the overall mean, y bar STR, and the standard error of the overall mean. And so the overall mean, remember, we said it's just a weighted average of the strata means. And the weights are given by the relative size of each one of those strata in the population. And so this is what you get, 1.932 millions. And I wrote it differently here. I put 1 minus f, but this is the same as the finite population correction factor I had in the other one. Different way of writing the same expression. Sorry about that. But this is the formula we had before. And if you do all those calculations, you get points. And by the way, here I got the 0.95. This 0.95 corresponds to 1 minus 0.05, which was the same for all the three strata. So I just took it out of the sum here. And that's why it's out here. And so we end up with 0.076, which means what? That with 95% confidence, the average dollar amount in each one of the 1,000 transactions is between 1.78 and 2.084 millions of US dollars. And by the way, if I wanted to know the total amount of money involved in this operation, I would just have to take 1.932 and multiply by 1,000, because this is my best guess of the average amount of the value, the dollar value amount of each one of the transactions. Okay, last I'm going to talk about making inferences about the population mean when we have a cluster sample. And again, you know, the calculations get kind of icky, but it's just a matter of looking to see what is it that we're doing. So recall cluster sampling, right? In a sense, it has some similarities to stratified sampling, but not quite. In stratified sampling, what we do is we take the entire population, which is heterogeneous, and divide it into the homogeneous components. So the strata here are the subgroups in the population. And so we would expect that the strata are relatively homogeneous. Here we take the population and divide it into clusters that are not necessarily homogeneous. And we do this to, you know, this cluster sampling is not a desirable way to sample. We do this when we don't have a choice. And so let's suppose that you have a container with I don't know, 100,000 boxes full of something. And you don't really know how many items are in each box. So there's no way for you to enumerate every item in that population without opening every single box and counting every single item and labeling every single item in every single box. And that's the last thing you want to do. So in this particular case, to save yourself the trouble, what you would do is you would use this cluster sampling. You would assume that each box is a cluster. And so you would just draw boxes. And then only for those boxes you drew would you go inside and count how many items you have, and then do sampling of those items. And so cluster sampling is not desirable, but it's something that sometimes you don't have, sometimes it's convenient. And the clusters here can be heterogeneous, so the items in a cluster may be different. So for example, let's suppose here's a typical use of cluster sampling. Let's suppose that my population is every household in Iowa, and there is about 1.3 million households in the state of Iowa. And, you know, households change, right? You know, new houses, old houses, families that are created. And so this is, keeping a good enumeration of every household in Iowa is really difficult. And so people don't have a good enumeration of every household in Iowa. And so if you want to measure something in a household, what you might do is you might cluster these households into some sort of administrative units. And typically what these population surveys do is use what's called a census block. This is an administrative unit that exists in every state. And in fact, in Iowa, there's about 216,000 census blocks. And so what you would do is you would draw randomly. So you call each one of these blocks a cluster, and you would draw these blocks instead of the individual households. And then within each one of those blocks, you would count and label, enumerate the households. So here's an example visually. I took this from Penn State. They have this good online Masters of Statistics course. And so here we have a case where, imagine this entire thing is a population, and each one of these big rectangles that are marked by thick black lines, this is a cluster. And each cluster contains all the little units that are separated by little gray lines. So in this, so each cluster is what we call a primary sampling unit. Each unit within the cluster is what we call a secondary sampling unit. And so let's suppose that you sample clusters, and the ones that we sample are the yellow ones marked here. And C here, I will use C to denote the number of clusters in the population, and N sub I would be the number of units within each cluster. So in this particular case, and M here, big M, is going to denote the number of sampled clusters. So in this particular example, there's 50 clusters in the population, so C is equal to 50. Each one has 8 units, so in this case, they all have the same number of units. You don't have to have that. And so the total number of units of secondary sampling units in the population is, in this case, the sum of the cluster units over all clusters. That gives you 400 units. Now, suppose that we sample M of those clusters, and in each one of those M clusters, so in this example, we sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of those yellows is a sample cluster. And we measure the whatever it is we're measuring in each one of the units inside each one of those clusters. So if we were to measure every unit in the population, which of course we won't, the total value, which is the sum of all the measurements, is what I'm calling tau here. It would be, look at the Y in the jth unit in the ith cluster, add them all up within the cluster, and then add those values up over all clusters. But we don't do that, right? Because we don't look at every unit in every cluster. We only look at every unit in the sampled clusters. So how do I go about estimating this tau? Well, first I'm going to compute the total in each of my sampled clusters. And so this is what I'm calling T sub I. And in my case, I have 10 of these T sub I's because I have M equals 10 sample clusters. And then I'll get the overall sample average. I'm going to call that Y bar. And that's just the sum of all the T's divided by M. And then I will estimate that population total, and I'll call that tau hat simply by taking the total number of clusters in the population times the per cluster average I computed from my sample. So here's an example. So let's suppose I have a container and there's 10,000 crates of similar size, and each one contains boxes. And in each box, I know there's contraband ammunition. And so what I want to know is estimate the total number of rounds in this container. And so here, what I'm going to do is crates. So 1,000 of those are the PSUs or clusters. And the boxes within the crates are the secondary sampling units. So, and the measurement for each box is just the total number of rounds. That's what the Yij is going to be. So C here is 1,000. There's 1,000 clusters in the population. M is 10, let's suppose that I draw 10 crates out of this 1,000 crates. And the sampling fraction here is 0.01. It's the number of crates I draw divided by the total number of crates. And so this is my first stage sampling fraction. The second stage, depends on what I do next, right? So once I have the 10 sample crates, I could, for example, count the number of boxes in every crate. And let's suppose that I find that each crate has a slightly different number of boxes. So the number of boxes in crate 1 is N1, and in crate 2 is N2, all the way to N10. And so the entire sample is going to have the sum of these within cluster totals. And those, so there's a total of little n secondary sampling units in my sample. And so in each one of these crates, I open each box, count how many rounds there are in each box, and this is my observations. And again, you have totally invented data in an Excel file that's called cluster example data XLS. And every calculation that I'm doing here has been programmed into that sheet, so you can follow afterwards if you would like to. So, all right, so the total number of PSUs in the sample is M, that's the 10 crates I sampled. The total number of SSUs in this particular sample is, in this particular set of crates is 1,603. There's 50 rounds of ammunition in each one of the boxes I opened. So that's true for every SSUs. And so the total number of rounds in my sample is about 80,000 rounds. And so Y bar here is the average number of rounds in each crate. And so that's just T, the sum of all the T's, which is this big T divided by M. And so Y bar here is 8,015. And so my estimate of the total number of rounds in this container is 8,015 times the total number of crates. Okay, so how do I compute the standard error? Well, I'm not going to go very deep into this. It gets tricky because I have to, well, let's just say that to know how to derive these formulas, we would have to know a whole lot more about sampling theory, and we're not going to get here. But trust me, the variance of this estimated population total is computed in this way: C times C minus M times this S squared U divided by M. S squared U is just the variance of the sampled crate totals. So you just compute S squared U in the same way. So you take your M crates, in each one of them, you compute the deviation of the total from Y bar, square that, and divide by the number of crates minus 1. So this is the usual way you compute a standard deviation. And so if this is the variance of tau hat, then the standard error of tau hat is just the square root of the variance of tau hat divided by M. So here is a few observations. I said that cluster sampling is not a desired approach. This you do when you really don't have a choice. And in particular, you don't have enough information about the population in order to design a better sample. The reason is that cluster sampling is not very efficient in the sense that the estimators that you get tend to have higher standard errors. So your margin of errors are going to be larger when you base them on a cluster sample than on some other type of sample. Stratified samples are pretty efficient in this sense. They typically give you more precise estimates than simple random sampling does. But cluster sampling does the opposite. You're better off doing simple random sampling most of the time than doing cluster sampling. So a strategy when you don't have a choice is to make M as large as possible. So sample as many clusters as your budget allows, And in order to keep the budget under control, subsample the secondary sampling units within these clusters, the M clusters that you drew. So so instead of taking a measurement, instead of opening every box, randomly sample boxes within a cluster, and that will allow you to have more clusters in your sample, and that will make your standard error lower. So you always want to maximize the number of clusters you can afford to sample. And the other thing you can do is make sure that the clusters you construct, because these ones you construct are as similar, are as homogeneous as you can make them. Sometimes you cannot do that. Okay, so here's a summary then. If you have a probability sample from a population, then you can use the sample observations to make inferences about population quantities, which is very desirable. If you want to be a good person, make sure you attach a measure of uncertainty to your point estimates. Point estimates can be very deceiving. And so you always should have some sort of a margin of error. And remember that in most cases, in real life, you will, when you're sampling without replacement and when the population from which you're sampling is not so large, you are going to have to use a finite population correction factor like we've been doing here. The other thing to remember is that there's so if we want to minimize the margin of error in our estimates, sample estimates, there's going to be the best way to go about this is going to be to play with a sample size. But when we have high variability of the attribute we're measuring in the population, we are going to have to compensate for that with larger samples probably. Okay, so now we're going to get into sample size calculations, and this is excellent. Okay, so why do we worry about the sample size? Well, we worry about the sample size because the sample size n is going to be proportional to the precision with which I can estimate the population quantity. And so remember what we just discussed, right? So we talked a lot about standard errors of estimators because the standard errors is what tells us how variable our sample estimator is going to be from sample to sample. We don't want high variability from sample to sample because we want to be confident that the one sample we have drawn is going to result in an estimate of the population quantity that is close to the population quantity. So in addition, so we really want to get an estimate that has a small standard error. And the standard error is always larger when n is small. So one sure way to increase the precision of your estimate is to increase your sample size. And so then the question is, should we get a sample that is as large as our budget allows? And the answer is no. You know, oftentimes you don't need a sample that's super large in order to get acceptable precision. Getting a sample that's too large is a waste of resources. And in fact, in some cases, it might unnecessarily expose you or somebody else to, you know, nasty substances, analyzing things that are icky. And so there's a sweet spot in terms of the sample size. This is a Goldilocks situation. We don't want, you know, too little is bad, too big is bad. There's that sweet spot. And that's what we're going to be talking about today. And here's a fun fact. The best sample size, or that sweet spot, is independent of the size of the population, as long as the population is reasonably large. So, you know, what is an optimal sample size in a population of size 10,000 is also going to be optimal in a if that population was of size 2 million. So that's kind of a fun fact. This is going to date me again, and I don't know if Jeff is here, but who remembers the magnificent Karnak? The magnificent Karnak was Johnny Carson. And remember, he always was guessing something, and he had this envelope, and he brought it close to, he sort of brought it close to see whether he could guess what was on the envelope. Sometimes he would blow on the envelope. And what I'm trying to say here is that coming up with the right sample size is not a Karnak thing. There's methods that we can use in order to come up with a good sample size. And so what are we going to do? Well, there's a method to the madness. So the goal here is to obtain the sample size n that we need in order to what? Well, here's where you come in. So the first thing you need to think about is what is it that you want to do with the sample? Are you interested in estimating a population mean? Or are you working with a categorical variable and trying to estimate some population proportion? Or maybe you have a different question in mind altogether, and we'll talk about that in a minute. So that's the first thing you have to think about. The second thing is, what is it that you're wanting to accomplish? So if you were thinking about what's my ideal sample size, what do we mean by ideal? So perhaps if you're estimating a population mean, perhaps you would like your sample mean to be within, let's say, 5% of the true mean with high confidence. Or if you're estimating a population proportion, maybe you want your sample proportion to be no further than, let's say, 0.04 from the true pi with high confidence. And so in both cases, what we want to, so these could be our goals, the criterion that we want to satisfy. And in both of these cases, what we would like to get is the smallest sample that will allow us to achieve that desired margin of error with a specified confidence. And again, if your confidence is very high, if you want to be very confident that you're within, let's say, 5% of the true mean, your sample size is going to increase, the required sample size. If you're not so concerned, you only want to be 90% confidence that you're within plus minus 5% of the true mean, then your sample size doesn't have to be that large. So that's where we're going next. So remember the notation we used last time around. So the population size n, the sample size little n, sampling fraction little n over big N, the measurement on a population unit, the measurement on a sample unit, the average, the sample average, the population average, the sample standard deviation, the population standard deviation, the number of positives in a population, the number of positives in a sample, the proportion of positives in a sample, and pi, which is the proportion of positives in a population. So this is just as a reminder, because we'll use some of these terms. We've been using them all along, so you should remember. But let's talk about the sample size we require to estimate a population proportion with a desired precision. Okay, so this is the simplest case. So suppose that I have, so for now, let's forget about the sampling without replacement and the small population. Let's suppose that I have a large population for now. This is the easiest case. And so I don't have to worry about this finite population correction factor because n is big. So let's suppose I draw a simple random sample. And remember what we have, right? So my point estimate of pi is just the number of positives in the sample divided by the sample size. And the standard error, remember, was just p, 1 minus p divided by n, square root of that. So remember, a 95% confidence margin of error is just 2 times the standard error, or 196 times the standard error. And so let's suppose that I want a margin of error that's no larger than 0.04. So I want my p to be within 0.04 of the true pi with 95% confidence. Well, what am I going to do? So this, if the margin of error is 2 times the standard error, and I know that the margin of error is 0.04, then I know that 0.04 is 2 times the standard error. And so if I solve for p here, sorry, not for p. If I solve for n, so I first of all take squares on both sides of this equation so that I get rid of the square root. And then I multiply both sides by n and divide both sides by 0.04. This is what I get. So the n here, the n that will give me a margin of the desired margin of error is equal to p 1 minus p divided by 0.04 squared. Of course, I don't know what p is until I get the sample. So I seem to be sort of stuck here. So what do I do? Well, oh yeah, so here's what I was just telling you what I did. So what is the value of p? Well, what I'm going to, since p is unknown until I draw my sample, I compute it, what I'm going to do is I'm going to think about the worst case scenario. And the worst case scenario is p 0.5, because that is the value of p that maximizes this piece of the equation here, and for which I'm going to need the larger sample size. So so normally what I would do is I would plug in 0.5 here and compute n. And so this is what that expression looks like. And so let's suppose that I want, this is an example, I want a margin of error that is no longer than 0.03, confidence 95%. This is how I do the calculations. So I'm using 1.96 instead of 2 here. But what I would need is I would need a sample size of size 1,000 from this population. And so you would round up, 1,068 is the sample size you end up with. I don't know how many of you guys pay attention to this, but if you think about all those political polls when they tell you, you know, Biden's approval rate is blah, plus or minus 3%, that's what they're doing, right? And the sample is usually about 1,100 respondents. And if you wonder why 1,100 respondents, it's because those people are doing this calculation. And so that's how they know how many respondents they have to contact. So if you have a sample size of 1,068, you can expect p to be pretty close to pi. In fact, no further out than plus minus 0.03. And so, for example, if p was 0.72, you are 95% confident that the interval 0.69 to 0.75 actually includes the true pi. And so, but you have to, I mean, 1,000 is a pretty large sample. So how do I save if I don't have the budget to draw a sample of size 1,000? Well, I could, for example, sacrifice a little bit of precision. So instead of 3%, I was willing to go down to like 4%, plus minus 4%. That cuts my sample size to 600. And if I was willing to live with 5% margin of error, that cuts my sample size to 385. And so if I also know that pi is likely to be either pretty high or pretty low, so not close to 0.5, then again, I can reduce the sample size, because instead of plugging in 0.5 in that expression for n, I could plug in, let's say, 0.75 or 0.9, if that's what I think the pi is likely to be. And so even for a margin of error of 3%, plugging in 0.75 instead of 0.5 would reduce my sample size to 800, and plugging in 0.9 instead of 0.5 would reduce my required sample size to 385 and still give me a margin of error of 3%. So this is how you start making calculations about what you can afford to do and what that means in terms of the precision with which you're estimating anything. So here's a little, whoops, sorry. So here's a little table that I computed for you. So if this is, so here we have the true value of pi, and it really in the population, and it really, you know, the other side of the distribution, you get the exact same results. And here's margin of error of 0.01, so really low margin of error, 1%, 90% confidence, and all the way to 10% margin of error, 90 or 95% confidence. And you can see when pi is equal to 0.5, you go from like 9,600, sample size of 9,600 to sample size of 96 when pi is 0.5. When pi is 0.98, the difference is not so big. So even in the worst case, you need 753 observations. But you know, if you are willing to live with, let's say, a 5% margin of error, you can do with like 30 observations. So there's a dramatic difference depending on what your margin of error is and what your desired level of confidence is going to be. Now, unfortunately, this is when you have, this gets really weird. This is when you have an infinite population, but oftentimes you don't. And so now you have to worry about this finite population correction factor. Remember, n minus n divided by n minus 1. And the margin of error here is going to be the 196. This is just O2 if you're looking at it for 95% confidence. And this is the, remember, this is the standard error when you have a hypergeometric random variable. So now we don't have that binomial model anymore. Now we have this hypergeometric model. And now we can still solve for n, but it gets a little messier because there's an n here and there's an n here. So if we want to solve for n, so I fix the margin of error that I desire. And now I have to solve for n, and I can do that, but it gets messy. And this is the expression that I find. Eeky. And so, you know, the z here is just 1.96 for a 95% margin of error. Sorry, confidence level. I still have the p, 1 minus p. So this piece here looks like the expression for n I had when I had an infinite population, the one that we just saw before. This is exactly that. And that exam expression appears down here. So in principle, so let me go to the next page. So this is what I was just saying. This here is the n, the expression for computing n if I was forgetting about the finite population correction factor, and this is the same thing. And so let me call that n sub 0. So n sub 0 here would be the sample size I would need if I could assume I had an infinite population and sampling with replacement. And so then the n, the expression for the n correcting for finite population and sampling without replacement looks a whole lot less ferocious. It looks like this. I take the n I would compute in the simplest case, multiply by the population size, and then divide by this expression over here. It looks a whole lot nicer than this thing over here. Okay, so here is using the n0 that we had from the tables before. Here's what the sample sizes you would require if you had a population of size 1,000. And when pi is very high, the values are kind of similar, but although at the bottom here, they don't change much, they do change in the top over here. All right. So what if we want to estimate? So that's what I'm going to say about a population proportion. When I want to estimate a population mean with a desired precision, one problem that you will find is that most everybody has inadequate sample size. This is what really grinds my gears. And so what do we do? Well, something very similar here, right? So now our measurement y is continuous, and the approach is going to be similar. So the margin of error here, when I'm thinking about y bar instead of a p, I don't know how many of you guys remember that instead of using the z-score, we use this t-score. It's kind of similar, but this one is a little bit more conservative in the sense that the t's tend to be bigger values than the corresponding z's. And so, but the margin of error is just this value that has to do with my confidence level, and then the standard error of y bar. And again, I'm pretending here I don't have a finite population correction or anything like that. So if I solve for n, this is what I get. The problem here is that now this also depends on n. So what I'm going to do is sort of close my eyes like this and plug in the corresponding z that I used before, even though what I really need here is a t. And so the solution here is to use z like we did before. And we also need to have an estimate of the variability in the population. In the case of the proportion, we had to know p, or we had to have some sort of sense of what p was going to be. Here we need to know, we have to have a sense of what the variability of the variable that we're using is in the population. And sometimes you have this information from prior studies or prior samples you may have gotten, or from a tiny pilot sample you obtained just to get an estimate of S squared. So the two solutions then is to either get some value from the literature or from your own experience, or to get an approximation using to this S squared using what's called the empirical rule. And the empirical rule is very simple. If the measurement you're taking, if this variable you're working with is kind of normal, so the distribution is kind of symmetric, then you would expect that 95% of the values fall within y plus minus 2 standard deviations. Remember the 68, 95, 99.7 rule for the normal random variable. And so one thing you could do is you could carry out a tiny pilot study and compute the approximate this S using the range. So the range is just max minus min. And so an approximation to S from a tiny, tiny, tiny sample is the range divided by 4. And that has to do with this picture over here. Here you have a normal distribution. Here's the mean. Here it's X bar instead of Y bar. And then if you go 2 standard deviations away from the mean in either direction, remember you get 95% of the observations in here. So the range is just the max minus the min. The range is just the max minus the min, and you divide it by 4 because you want to estimate, you get an estimate of S. Okay, the last thing I want to talk about today is what happens when you have a different. So what happens when you have sampling without replacement and your question is a little different. So sometimes let's suppose that you have a situation where you see 10 minutes. Okay, I'll be fine. You have a situation where you seize a shipment, let's say, of pen drives that may be concealing child pornography. And so, let's say, and so let's suppose that there's big N drives in the seizure. How many of those carry pornography? And you don't really want to know exactly how many carry pornography. What you want to answer is how big a sample do I need to draw such that I can say that at least K% of the drives in the population contain illicit photos with some confidence level, let's say 95% confidence level. So sometimes you don't have to come up with the exact value of the proportion of pens. Sometimes for sentencing purposes or what have you, it suffices for you to say, I'm pretty confident that more than 85% of the pen drives in this population contain child porn. And so let's suppose that K is 85 here. Let's say 85% of the drives contain child porn, and alpha here is 0.05. So I want to be 95% confident that at least 85% of the drives contain child porn. Then what is the N that I need in order to answer that question? Well, the N, to compute that N, I'm going to use this hypergeometric probability model that we talked about earlier. And clearly, N is going to have to be larger for larger K and smaller alpha. So the more confident I want to be, and the larger the proportion of pens in the population, I want to say contain child pornography is, the N is going to increase. So the hypergeometric model, we introduced this model like in slide 77. We didn't talk about this, but if I want to, so if X here is my variable, the number of positives, has a hypergeometric distribution, what does that mean? I can compute, what it means that if I have the following information, the sample, the population size, big N, the number of positives in the population, that's K, okay? No, the proportion of positives in the population, I think. And then here, this is the sample size, which is what I want. And this is the proportion, X is the number of positives in the sample. I can compute, if I knew all that stuff, I could compute the probability of observing a certain number of positives in a sample of size little n. So in order to undo this and find out what is the little n I need to get in order to be able to say that the number of positives in the sample in the population is at least this many, what I am going to do is I need to, what do I need to do? I need to, first of all, come up with a K I want. So 85% of the items in the population are positive, or 90% of the items in the population are positive, or 57% of the population items are positive. So that's my K. And then X here is going to be the number of positives I expect to see in the sample of size little n. And so if K is close to 100%, then I would expect to see that, to see almost 100% of my sample items to be positive also, right? So oftentimes what we assume is that when K is very large, I expect to see the same number of positives in my sample that there is in the population. So how do I do those calculations? So it turns out that we could solve for the, so using this expression over here, we could solve for little n, given a value of K and big N and so on, but it's very difficult to do by hand. And so there's software that's available to do this. And there's one that's called the Hypergeometric Sampling Tool that was published by MC, the Europeans. We have that in the website for the course. And Joe is going to go over this next Friday. But here, 5 minutes. Ha! Okay, so Joe is going to go over this next Friday. And I can think of two possible situations here. One situation is when all the n sample items are successes. And another situation is when one or more sample items are failures. So for example, imagine I draw a single pen drive and there's no child porn. Well, that immediately tells me that the proportion of pen drives in the population that contain child porn cannot be 100%, because I drew one and it didn't. Now, if I draw one and it does, that means that it's still possible that everyone will have child porn. And so the more positives I get in my sample, the easier the smaller the sample I'm going to need in order to say that with 95% confidence, K% of the items, at least K% of the items in the population are positive. So here's, and I have just a few more slides and then I finish. So these are all values. This is from the UN guidelines for drug sampling. And what they have done is they have used this model to compute, to give you some sense of what the sample sizes would be. So if you have a population of, let's say, size 10, and you want to be able to say that at least 50% of, at least half of these items are positive, with 95% confidence, you would only need a sample of size 3, as long as all 3 of those items that you draw are positive. And if you want to say that at least 90%, 9 or more, so are positive, then you would need to draw 8 positive values in your sample in order to say that. If you want to increase your level of confidence, of course, your sample size increases. If you have a population of size 200, let's say here at the bottom, notice that the sample size that you need doesn't increase a whole lot. So if you only want to say that at least 100 of these items are positive, then you only need to, with 95% confidence, you need a sample size of 5, very low, as long as all 5 are positive. If you want to say that at least 90%, so 180 out of the 200 are positive, you only need a sample size of 26, as long as all 26 items in your sample are positive. Now, okay, so this is the same thing, but with larger populations. You see that even if you're, the sample size doesn't change very much if, regardless of the size of the population here. So even if your population has 10,000 and you want to say that at least 90% of those are positive, you only need 29 items in your sample, as long as every last one of those is positive. Now, the problem gets when some items in your sample are negative, because suddenly your confidence goes down. Your confidence goes down. And so let's go back to 95% confidence, and I want to be able to say that at least 90% of the items are positive. If I draw a sample and one item is negative, then I'm going to have to look, and the population size is 10, I'm going to have to look at all 10. So, and in fact, if 2 of them are negative, that goes my 90%. That's no longer possible. If the population size, let's say, is 200, and I'm going back to this 0.09, remember when every item was positive, I only had to look at 23 of them. But if one item is negative in my sample, I'm going to have to increase my sample size to 40. And of those 40, only 1 can be negative. If I get 2 negatives, to keep my 95% confidence, I would need to have at least 53 items in my sample. And of those, only 2 can be negative. And so the more negatives I get in my sample, the larger the required sample size is going to have to be for me to maintain my level of confidence. Of course, if I keep the same sample size as I had before, let's say 23, and I observe some negatives, what happens is that my level of confidence goes down. And so that's what we see over here. So here is a sample size of 23. Remember, that was the optimal if I wanted to say at least 90% are positive in a population of size, let's say 100, with 95% degree of confidence. And so if I get no negatives in my sample, this is this curve over here. And so this is the 95% point. If I get 1 negative in my sample and I have a sample size of size 23, my confidence level goes down to like 78%. that there's at least 90% positives in the population. And if I get 2 negatives in my sample of size 23, my confidence level is less than 50%. That there's at least 90% positives in the population. So the confidence level changes a lot if you in that particular situation. So I can't believe this, but I am only 1 minute behind. This is a first for me. Okay, so next Friday, what we're going to do is we're going to talk about the frequentist versus Bayesian approaches to calculating sample size. And I am not going to go into any depth. I am just going to go over some of the stuff you're likely to run into in the literature and just give you some guidelines of what's the difference between the Bayesian approach and the frequentist approach, which is what we have been doing, by the way, frequentist approach. And then I don't know if, depending on how many slides I prepare for this, I'll go on to some odds and ends, because I want to leave plenty time for Joe, at least an hour and a half, for him to do examples and show you step-by-step calculations. So without further ado, I am going to say bye-bye until next Friday. And thank you so very much for sticking with me.
Alicia, thank you again for joining us for a second session today. And I know that we look forward to what the third session brings, both in terms of educational material and practical material. Thank you all for joining us. We hope you have a great day.